So let us try to understand alpha beta pruning by taking the same game tree that we had used to illustrate the minimax procedure. But then one thing to notice at this point of time is that we do not evaluate all the leaf nodes. So we start by computing the static values one at a time. We compute the first static value, which is 4. Now immediately we have a realization that one level up, that is the min, any value here that he would be looking for would be less than or equal to 4. We then compute the next value and realize that this value is 5 and therefore mean can stay with 4. Now one level up, when we want to back up, a realization comes that if Max had taken this path, then he would have been at least guaranteed 4. That means at this point of time Max can have values which should be greater than or equal to 4. We compute the third static value, which is 1. At that point of time we can see that the mean value now would be something which is less than or equal to 1. This is where a little introspection will make us realize that this side on the left, if Max wanted to go, he would have at least 4. 4 or something greater than 4 is what his current value is. Whereas if he prefers to come to the right, all he is guaranteed is something less than or equal to 1, and therefore he would never prefer to come this way. That is as good as saying that this side of the tree does not exist for him. So he can think of throwing away all of this, because as if this tree does not exist. Why is it that this tree does not exist for him? This is because if Max follows this path, let me repeat this, if Max follows this path, he will have 4, and if Max comes on this path, all he is guaranteed to have is something which is less than or equal to 1. Therefore this tree does not exist for him, and once he can cut this tree out, he can update that value to be really 4. So we have got to the same result as in the minimax procedure, but then we have not evaluated even this node. So these values that we have cut out, these cannot affect the value of the root node. So the essence of alpha beta pruning is that the cutout sections of the search space, they do not affect the value of the root node, and we therefore do not need to compute these values which have been cut out. So alpha beta pruning, we need to realize this, that it is not a separate algorithm. Alpha beta pruning is actually a layering on top of minimax. It is an optimization procedure on top of minimax to reduce search space and somehow get to the same value that we have got in the minimax procedure. Alpha beta pruning therefore reduces the computation time by a huge factor. This allows search much faster, and then we can even go deeper into the game tree. That is, if we had thought of only computing up to level 4, alpha beta pruning would allow us to compute to the double of that level. It cuts out branches in the game tree because these need not be searched. There already exists a better move. Now it is called alpha beta pruning because it passes two parameters in the min max function, one called the alpha and the other called the beta. We will now focus on what is alpha, what is beta, what is an alpha cutoff and what is a beta cutoff. When we are doing minimax procedure, the minimax traverses the search tree in depth first order. That is what we have seen. Now, the alpha of a particular node n is the best value that max currently can guarantee. So, this is the maximum value found so far, whereas beta n is the best value that mean currently can guarantee. So, it is the minimum value found so far. Now, having defined alpha and beta, let us see when we cut out branches of a tree, which is called an alpha cutout and which of the cutouts are called a beta cutout. So, in order to define beta cutoff, let us take a sample tree. Now, let us assume we have a max node n and cutoff search below n is not required. Cutoff below n is possible if alpha n is greater than or equal to beta I. Here by cutoff we mean that we do not generate or examine any more of its children. So, let us take some values for the leaf nodes as shown, 4 and 8 there. Now, because this is a mean node and this is a max node, so the values that will be possible is this node will be greater than or equal to 8, whereas this one will be less than or equal to 4. Now, recall what we meant by an alpha and a beta. The alpha is the best value the max currently can guarantee. So, it is the maximum value found so far. So, at this node we have alpha equal to 8. Beta is the best value that mean currently can guarantee. So, beta is the minimum value found so far. Now, let us look at this condition given here. So, I have my node n here and the alpha value of n is 8, whereas the beta value of I, which is an ancestor of n, is 4. So, the alpha of n, which is 8, is greater than or equal to the beta of I, which is 4. The condition is satisfied. That means we do not need to search anything beyond this line, and this is called a beta cutoff. Now, why is that we do not need to search anything beyond this point? It is interesting to take 1 minute and note it. Here we are guaranteed to have something which is greater than or equal to 8, and given that guarantee, here we have something which is guaranteed to keep me to the maximum of 4, because this is a mean node. So, it will only look for 4 or something less than 4. So, that means there is no point of looking for a better solution in this subtree, and that is what is a beta cutoff. Next, we will look at what we mean by an alpha cutoff. So, given a mean node n, we would love to cut off search below n when the beta is less than equal to alpha of I. Let us take a small portion of a game tree to understand this, and let us mark the leaf nodes 3 and 2. Now, this is a mean node, so it is guaranteed that it will have something which is less than or equal to 2. This is a max node, it will have something which is guaranteed to be more than or equal to 3. So, that is greater than equal to 3, that is less than equal to 2. Under such a scenario, if I am looking for coming along this path then I can only have things which is maximum of 2. So, for max here, there is no point coming this path, as if this does not exist for him, because if he takes the left side, he will get 3. If he somehow takes the right path, all he can get is a maximum of 2. So, there is no point looking at this portion of the tree, and this cutoff is called a alpha cutoff. Now, to check the condition, recall that alpha is the best value the max can have. So, we have an alpha of 3, beta is the best value that mean can currently have. So, we have a beta of 2, and now if you compare the beta value at the nth node, which is 2, and which is less than the alpha value of its I ancestor, we can have this cutoff, and this condition is satisfied. So, such a cutoff is called an alpha cutoff. Next, let us take a more complex game tree and try to understand alpha beta pruning. Taking a complex tree and understanding it is important, because there are few things that does not come out in a very simple example that I have been showing. So, let us focus our attention on this tree here. All its leaf nodes are marked, and let us start with the mean node here. So, if you look at the mean node there, I have 8 and 5. Mean expects that the minimum should come, and I know 5 should be there, but then I am doing a depth first search and I am doing alpha beta. So, here I will first give mean the value that it could be something which is less than or equal to 8. The moment I see the next leaf node, which is 5, I revise that value and say that it is not 8 but 5. I back that value up one more time, and now at the max level here, I can write that it should be greater than or equal to 5. Thereafter, look at this portion. Here we have the leaf node 3. So, mean should be less than or equal to 3. Once I realize I have here less than or equal to 3, and this is a max node which realizes that if it moves this path, it will at least have 5. So, it will not love to come this side. So, as if this whole subtree does not exist for it. So, it will have a cutout there, and once it has a cutout there, we cut off this portion. You need to realize that I will no longer need to evaluate this, and therefore, I no longer need to look at that node. I back up the max value to the mean level, and before that I need to have a realization that because there is no right sub tree, so this value can be 5. I back that value up, and because this is a mean node, I would have a value which is less than or equal to 5. I come down at this portion now. This is a mean node, so its value is less than or equal to 9, and then when I see 7, I know that this has to be overwritten and I should get to the value 7. So, the correct evaluation of this node is 7. This 7 is backed up, and I have the max value which is greater than equal to 7, and now there is a interesting realization, which is that if mean comes this side, it would have values which is 5, but if it follows this, arrives at this node, then all mean will have are values which are greater than or equal to 7. Now, the idea for mean is to minimize, and therefore, if I have a subtree which guarantees that the value is going to be at least 7 or more, then when I am searching as mean, this subtree is as good as non-existent for mean. So, we will have a cutoff there. Now, when we have a cutoff at that point, what we no longer need to evaluate is not only the leaf nodes that I have marked, this one and this one here, but also a generate function, which is I do not need to generate the children of this particular main node. And that is an amount of saving that alpha beta pruning allows, not only reducing evaluation of the leaf nodes, but also reducing generate functions. Now, once we have that value and this right side of the subtree is not there, so we can back up this value here as 5, and once that value is 5, the max node has a value here which is greater than or equal to 5. Now, let us focus our attention on the right subtree. At the root, I have 5 coming from the left side, and I start with the leaf node here, which is 1, back it up to the mean level. So, I have something which is less than or equal to 1. Now, this is where it becomes very interesting, and this one would not have been visible in a small tree. Here I have a root node occupied by max, where if I visit the left tree, I would have 5, and I am expecting something greater than 5 by visiting this side of the tree, the right side of the tree. Now, when I realize that this tree here, all it will give me is maximum of 1, I can cut this tree out. One difference that you should notice now between the earlier cutouts and this cutout is the fact that earlier cutouts were done on adjacent levels. This cutout is called a deep cut because I have gone at least 2 levels down the line to cut out a subtree that I will not explore any further. Taking the discussion forward, if you now focus on 6 here, the mean is guaranteed to have less than equal to 6. The next node is 9, but this is not going to satisfy this upper bound that mean has put. So, all I have is 6 here. This side of the tree which have been cut out does not exist for max. So, max would back up this value as 6. And now, focusing attention on the mean node, the mean will guarantee less than equal to 6 at this node. I have 9 there, so I have a mean node, so at least 9 less than equal to 9. So, I have a 9 marked here, and then this backs up to the max node, which is saying that it should be greater than or equal to 9. So, when I have a max node here which is greater than or equal to 9, and I have a mean node which is saying it is less than or equal to 6, then mean will rather go here and never come on this path. So, for mean, as if this portion of the subtree does not exist, and we can cut it out. So, we can have a cutoff here. Once we have a cutoff here, these leaves 3, 4 and this generation of children for the mean at this point is not required, and that's the amount of saving. So this is what we have at the mean node now, and now if you go one step up, you'll see that the solution of this is that Max prefers to take the right path because he has a greater than or equal to 5. So this side is 5, this side is 6. So he prefers this side that brings him to 6, and then goes down this path which is 6, and there goes down that path, and this is what Max does with the first best move that he has extracted from the minimax procedure and reduced search using alpha beta pruning. Now alpha beta pruning, the effectiveness is guaranteed by the fact that it is guaranteed to compute the same value for the root node as computed by the minimax with less or equal computation. Worst case, if we do not have any pruning, we end up examining b to the power d leaf nodes, where each node has b children, and we are talking of a d-ply search. In the best case, we examine only 2b to the power d by 2 leaf nodes. What this result means is that for minimax with alpha beta pruning, we can search twice as deep as we would have done with minimax alone. So let's say we were trying to get the first best move for a chess game, and we were looking at a depth of 7 with minimax, then minimax with alpha beta pruning, we can at least go up to 14. That's what the double means here. Now minimax algorithm and its variants are inherently depth first search. So there are improvements on minimax with alpha beta pruning by using some better strategies for depth first. Like we could have iterative deepening, which is used in conjunction with alpha beta pruning, so that a reasonable good move can be returned. Now using iterative deepening can give move ordering hints at shallower depths, and as well as shallow alpha and beta estimates. Now these can produce cutoffs for higher depth searches much earlier than would otherwise be possible. There are other algorithms that use the best first strategy for minimax with alpha beta. Now these are more time efficient, but then typically it is heavy cost in terms of space requirement. These we have not covered in our game playing algorithms and leave it out as exercise to be taken during the course of our study. In the next week, we will focus on knowledge representation reasoning and understand predicate calculus. Thank you very much.